We have added vectors graphically, which means we've just drawn them on paper according to scale. We've found the resulting vectors and we've measured them, and we've found the resulting angles, and we've used a protractor to measure them. Pretty inaccurate. There are other ways you can add them. Geometrically, you can put them together, and then you can use the sine law and the cosine law. But by far the easiest and most straightforward method is to use what's known as the components method. That is, break the vectors up into perpendicular components that have the same result, and then just add the components and put them back together. That way you're just using SOHCAHTOA. There's a lot less room for error. I've put together this example. This person walks 5 meters, 53 degrees, 5 meters north, 53 degrees to the east. And then they walk 13 meters facing north and rotating 67 degrees to the west. We could draw them out, try and get all the scale right, draw the resulting vector, which is going to start here and end here, try and use a protractor to measure that. Instead, what we're going to do, we're going to measure the equivalent northerly trip combined with the easterly trip, and then once again, the northerly trip combined with the westerly trip. Okay, so here's my triangle, 5 meters north, 53 degrees east. What I need to do is find the length of this adjacent side. And of course, that means I'm going to be using the cosine. And so the cosine of 53 is going to be equal to the adjacent side over the hypotenuse. Now I'm going to just say this is D1n for D1 north. So the length of D1n over 5 is equal to the cosine of 53. So 5 times cosine of 53 is equal to 3. So this trip, basically, I go 3 meters to the north. I prefer to keep track of all this information in a table so that it's easier to add up. And so D1 to the north is 3 meters. To find the length of this side, it's actually going to be the sine of 53 is equal to D1 to the east. So D1 east over 5 meters. And when I do the math, it turns out that this one is 4 meters east. I carry out exactly the same set of operations with this longer trip. And what I find out is that this is 5 meters to the north. And so this is a 5 meter trip for D2. And to the west, it's actually 12 meters to the west. Now, to keep everything north and east, what we do is we actually treat this as negative 12 meters to the east. And now I've got everything in the same direction. So altogether to the north, we can see that we're going 3 meters, and then we're going another 5 meters to the north. So altogether, we go 8 meters to the north. And when we're looking at going to the east, we go 4 meters to the east, and then we go negative 12 meters to the east. And so this is the same as negative 8 meters to the east. So my total trip in terms of components is 8 meters north and negative 8 meters to the east, which is the same thing as 8 meters to the west. Okay, last thing I need to do, and obviously this is not to scale, is I need to put together, wow, this is really not to scale. Okay, so let's just erase the whole thing. Because whatever our final trip is, it's the same as going 8 meters to the north, and then 8 meters, negative 8 meters to the east, which is the same as 8 meters to the west. And this is going to be a nice, easy triangle to do the math on. So I could use tangent first to find out what the angle is. The inverse tan of 8 over 8, or the inverse tangent of 1 is 45 degrees. So this is north, 45 degrees to the west, if I want to express it that way. And the actual length, I don't know what it is. It's 64 plus 64, 128. It's the square root of 128, which is some decimal. So altogether, this trip is 120, square root of 128 meters. And this is face north and turn 45 degrees to the west. That's my final answer. So break it into components with sine and cos. Add the components together. Use the table. It's a little bit easier. And then make your final triangle using your northerly and easterly components and figure out the dimensions.